thing. You hold it in the palm of your hand, does a wonderful job. And just as a general battery powered, lovely speaker, brilliant audio. $99.
Okay, I'm going to get a little bit of feedback here for a second.
Wonderful job. And just as a general,
just have to mute that. And we should be good. Okay. Well, with that in mind, we've got John Portune again, W6NBC, and John's brought us a topic, plastics and plastic assembly for ham radio home brewers. So take it away, John.
All righty, let's do the share screen bit here. We'll go there. Oops, no, I've got to go there first. There we are. And get that out of the way. Slideshow from, where is it? Oh, get out of the way. Well, it's there somewhere. Slideshow. Why isn't this working? There we go, from the beginning. Okay, now we got it. Okay, I assume you're all seeing the opening slide?
Yeah, very good.
Okay, turn this off. And by the way, if you want the slides, they're always available. All my stuff is always available. Just go to my website, w6nbc.com/slides, and you can download the PowerPoint pack deck. Okay. Most of you are aware of my mag loops made out of plastic pipe and foil tape, so I won't do any review here. But and of course the capacitors that I have been pushing there, which are not the usual vacuum variables or rotary capacitors at the top, but using PVC pipe and other things, sliding capacitors inside the loop and ones on the outside to make them much less expensive. So this one I've spoken on a lot around the circuit. This one is a 4-foot loop, my general purpose 10 through 20 meter loop. Anyway, and it uses an internal and an external cheap tuning capacitor, which works very well, by the way, a little piston inside, which is just a PVC pipe that runs inside that you can pull in and out with a piece of 1/2-inch pipe inside with aluminum on the aluminum foil tape on the inside that you can pull in and out for fine tuning, which by the way, I've learned recently, it's better if you make the slot at an angle, then you get a better fine tune. And then a bigger pipe, half pipe on the outside with aluminum foil on it too, which is a band set capacitor, so you can set the band as well. So this has been the aluminum foil and PVC pipe capacitor, mag loop that I've been talking a lot about recently. Anyway, that's not what I'm talking about here, but it's an example of using plastic to build ham radio projects with. And this shows the capacitor, outside capacitor to set the band and the inside capacitor to set the fine tuning. And here's a 6 to 10 meter version of it, which by the way is in the May-June issue of the Newbie magazine, the League's Newbie magazine on the air, which I've been writing a lot for recently. I haven't written too much for QST recently, but I've been writing for the Newbie magazine on the air. The editor, Becky Schoenfeld, who I've gotten to know very well, is not very technical, so she's quite appreciative of my help in writing the Newbie magazine. Been writing most of the project articles for the on the air, and this is in the May-June issue, which I think is the current. Maybe it's the last. I think it's the current issue. Anyway, it uses the same technique. You can see the band capacitor, which is under the top of the loop, and the fine tuning capacitor, which is on the top, which works very, very well. You can make a very easy to tune loop capacitor, mag loop here, without having to spend all the price for an expensive rotary, which has losses, and also a vacuum variable, which are hard to get these days, and also very expensive. Okay, but we had a major lesson to learn from this loop. One of my local Zoom group had a major lesson to learn about dielectric loss in plastics used for antennas and capacitors. Rob Janke, K0XL, has been building a lot of loops of this design, and also using a calculator, which if you don't have this calculator, you should get it for yourself. It's the VK3 CPU mag loop calculator, and you can get it just by just searching for the VK3 CPU mag loop calculator. It's one of the excellent online free available mag loop calculators, the best one I've ever seen. It comes up with graphs, all well done, very well done, and all the graphs are active. You take it, you can drag the bars, and all the graphs change when you change any one of the characteristics. So you can put loop size and duping diameters and everything you want about a mag loop into it. And when you drag the drag bars, all the other curves change for you. Wonderful, wonderful calculator. And don't worry about writing all of this down, because just go to my website and download these PowerPoint slides, and you'll get all this information for yourself. K5DCC Denny Johnson has built a lot of these mag loops and had wonderful results with them. But anyway, we had a major lesson to learn, though, about plastics. It all came out when in some of this experimentation with using PVC and aluminum foil to make mag loops. So we're going to show you a little bit of, to borrow from Mozart, a little Eine kleine polymer Physik based on his Eine kleine Nachtmusik. I speak reasonably good simple German, so I can say that Eine kleine Nachtmusik or Eine kleine Polymer Physik, a little polymer physics. And I found this kind of interesting because there are two kinds of plastics out there. And I think it's important for you to know this if you're a home builder and you're using plastics in an RF environment, because most of us think, if we're home builders, most of us think, well, if it's plastic and you put that in it, and you can use that in an RF environment, and it doesn't see the RF. Nah, that's not true. It's absolutely not true. Some plastics don't live well in an RF environment at all. And you might think, well, any plastic, RF goes right through it. Yes, the RF goes right through it, but not as well as you think it does, because sometimes the plastic burns up and creates a lot of heat. And this is something that you need to know if you're a builder. So don't just automatically think, oh, if I want to put a bracket out there and hold something in this new antenna I'm building, I'll just grab a piece of that plexiglass or some of that nylon or some of that PTFE or whatever it is, and the RF won't see it. That's not true. That is not true as we come out, because there's a property called the dissipation factor, symbolized by that Greek letter down there. I think that's a phi or whatever it is. I don't know the Greek alphabet, but that's the Greek letter, lowercase Greek letter. And this dissipation factor is very important when you're designing plastic material to be used in an RF environment. The reason is all molecules, including water, this is a water molecule, come in two varieties. Either they're polar molecules, which are non-symmetric. Water molecule is a good example. It's a non-symmetric molecule. One oxygen atom, two hydrogen atoms, and you can see it is not symmetric. The way the hydrogen atoms bond to the oxygen atom, they don't bond in line. In other words, the hydrogen atoms sit off at an angle to the oxygen atom, meaning that on one side of a water molecule is more negative, and on one side it's more positive. It's a non-symmetric molecule. So it's a polarized molecule. And the electrons, as they run around, and they do in the outer orbits of these atoms, they share the outer shells. Now, of course, hydrogen only has one shell, oxygen has several shells, but the electrons share the outer orbits, and they spend more time around the oxygen atom, meaning that one side is more polar, is more negative, and one side of this molecule is more positive. So it's a polarized molecule. Well, this is true of all molecules. And this is something we need to know. And this is particularly true of, and this is especially or genuinely true of plastics. Some plastics are polarized plastics or polar plastics. Some of them are non-polar plastics. And it's important to know this and which plastics are polar and which are non-polar, because the polar plastics aren't good in an RF environment. The non-polar plastics are good in an RF environment. For example, here's a Teflon molecule. Now, Teflon is a great plastic, or PTFE as it's sometimes called, polytetrafluoroethylene, PTFE, or Teflon is the common name of it. As you can see, there's a picture of the molecule. And as you can see, it's symmetrical. It's basically a lot of fluorine atoms coupled symmetrically to a lot of chlorine atoms, or carbon atoms, I'm sorry. So polytetrafluorine atoms, ethylene, PTFE is more the technical name of it. And it's a non-polar molecule. In other words, it's symmetrical. Polyethylene, for example, which is a very common plastic. Lots of things are made of plastic bags and stuff for polyethylene. It's also a non-polar plastic, as you can see, and you can see why it's non-polar, because the 4 hydrogen atoms and the 4 carbon and the 2 carbon atoms, I think they are, in it, are bonded together symmetrically. And you can see the way it's structured down there in the picture of the molecule. And it's a non-polar plastic or polymer. So here's a polar plastic, a PVC molecule. And you see PVC is a polarized molecule. It's got carbon atoms, hydrogen atoms, and 1 chlorine, polyvinyl chloride. And the chloride is that 1 chlorine molecule sticking out to the side, making it a polarized molecule. You can see why it's a polarized molecule when you see the picture of it, which makes it not a good plastic. Maybe some of you have heard this in the past, that PVC is not a good plastic for an RF environment, and that's true. And it's true because PVC is a polarized or a polar molecule. Now, this affects what's called the dissipation factor, or sometimes called the loss tangent. If this is a technical term, the loss tangent, you can see here. And it's because the loss tangent has to do with its loss factor. It has a reactance or an AC resistance caused by the capacity, but it also has a resistive factor in it, which is the R sub L of the plastic, and it creates you can see the loss tangent down here at the bottom if plotted out in a polar fashion. So if the loss tangent is 0, there's 0 loss. But if the loss tangent is as much as 90 degrees, then the loss is 100%. So depending upon this loss tangent in the plastic, the loss can be very high or the loss can be very low. And if the loss is high, the plastic will turn all of the RF into heat rather than going through the plastic. So plastics aren't necessarily immune to the RF going through them. So just because it's plastic doesn't mean it will ignore the RF. If you use a piece of plastic to hold up your metal conductors in an antenna you're building. So here's a nice little list for you that might be of interesting to you, listed according to loss tangent or dissipation factor, which is the same thing. Here's a list of which you can get this list by just downloading my slides, and you'll see that it's move this out of the way here for myself. You can see the various loss tangents or dissipation factors of common plastics. You can see the on top of the list are the non-polar plastics that we might be using. Teflon, of course, tops the list. It has the lowest of all dissipation factors of 0.0001. So it's a very low angle of dissipation, or loss tangent angle. Tangent, of course, just the geometric figure angle. Silicon sealant, for example, the clear stuff, the smelly clear stuff with the acetic acid smell to it, is a good plastic to use, by the way. So silicon sealant, that stuff that settles, makes that kind of rubbery substance, a good material to use for building RF free or RF suitable devices if you're building them. Low density polyethylene, the stuff that plastic bags are made out of, is a good plastic to be used for building things out of. And a lot of things are built out of low density polyethylene. And polypropylene, which is also a good, a nice 3D printing plastic, is a pretty good material. High density polyethylene, which is a good building material. Polystyrene, which is what coils inside of radios very often were made. All of those are good plastics for building with, and why they've been generally used in the electronics industry for building plastic materials. And high density polypropylene is a good 3D printing plastic. Polar molecules, by the way, ones that aren't so good, and you look at the difference between the low density, between the polar molecules and their loss factors, their dissipation factor, what percentage of the energy going through them gets wasted as heat, compared to the polar molecules, like polycarbonate, which is Lexan, very tough plastic. But look at how much loss there is in it. Why, it's 100 times as great as Teflon. 100 times as much of the energy that passes through them gets burned up as heat. And look at hot glue. You might think, oh, well, I'm building this RF thing, and I can use some hot glue to hold down this bracket that I'm holding up and building an antenna. 150 times the loss of Teflon. How about Mylar? Or PET plastic, which is the plastic bottles used for making plastic drinking bottles, using a plastic drinking bottle in one of your projects. Not very good. How about PC board? It's 170 times more lossy than Teflon. How about vinyl plastic tape? You might think, oh, I'll just use some plastic tape around this to make my radio project. Not very good. 170 times more lossy than polyethylene or Teflon, and certainly polypropylene or high density polyethylene. It's certainly 50 times more lossy. How about epoxy? You might think epoxy, oh, that's a great substance. I can put epoxy and hold my antenna tubes that I'm building here for my projects with epoxy cement. Look at that. It's not really that good, is it? How about plexiglass or acrylic? Oh, that's a great stuff. No, it's not great stuff. Get yourself some sign plastic or some acrylic and polymethyl methacrylate. That's what it is. It's not great plastic. And here comes the champion, the one that you all think and probably think is a great plastic for building RF projects out of. Nylon. You think nylon is a great plastic? Look at it. 360 times more lossy than Teflon. Now, what do you think about these plastics for building? Polar molecules are not great plastics. So if you want to build RF projects, well, Teflon is not a really good choice because it's pretty expensive. But low density polyethylene, polypropylene, polystyrene, high density polyethylene, these are materials that you might want to build with. And they're all very lossless or very low loss. So don't think that just because it's plastic, that PC board or Mylar or hot glue or ABS or epoxy or nylon are great plastics to build with. No, they're not. Not if you're really going to suggest them to hot glue or to RF environments. I'm going to show you here a project that we got into, that one of my buddies got into, that proved it very dramatically. Some examples of dielectric heating in plastics. The energy absorbing region of the water molecule is such that there's still sufficient dielectric loss to impair satellite TV reception at 10 gigahertz during severe rain. We all know this, that rain can bother antennas, and sufficient loss to heat a cup of coffee. Why do you think if you put a cup of coffee in a microwave that it gets hot? It's because it's a polar molecule. That's why. Now, here's an interesting chart for you. It shows the radio window in the atmosphere, how that between about 10 meters, and by the way, this frequency is back. These charts are backwards. Why they publish them this way? The high frequencies are all at the left and the low frequencies are all at the right on both of these charts that I took off the window, off the internet, by the way. And you can see that there's a completely transparent window from about 10 meters up to about 1 millimeter in wave, the microwave. And there's some microwave windows and then infrared. But then above that, in the visible range, the atmosphere becomes completely opaque. And you can see what causes it. It's various molecules in the atmosphere. It's just a little bit of physics here, caused by carbon dioxide and nitrous oxide and water and ozone. I learned here back a number of years ago, is a picture of me when I was young and foolish. Anyway, I lived near a company in Sierra Madre, California, that made most of the drop-down masks that fall down in an airplane when they need to give you oxygen, when they get to, if there's break in the cabin pressure. A company called Sierra Plastics. They mold the little oxygen masks that drop down, and they use an RF heat sealer. Well, they make them out of plastics that are polar molecules, and therefore RF is good for heat sealing. Well, Sierra Plastic. I was running a 10-meter repeater from my home time at that. You can see me talking on it there on the local transmitter. The receiver was 3/4 of a mile away at another ham site. And I had a phone line in between the two of them because I didn't want to run a 10-meter duplexer. I ran a two-site receiver 3/4 of a mile away, transmitter at my site. But this 27 megahertz RF heat sealer at Sierra Plastics, which was just down the street from me, was driving me crazy. But that's why they're using 27 megahertz to do heat sealing, because it was polar plastic, because they were running PET and PP and the plastic drinking bottle plastic and ABS to make their drop-down masks from. But now here's the eye-opening example that we learned why you need to pay attention to the plastics when you build things for RF environment. Good friend of mine, K0XL, was building this really great mag loop out of 5/8 copper tubing, which is sufficient for 6 and 10 meters, not big enough for lower than that, but at least big enough for 6 and 10 meters. He was 3D printing this nice little tuning capacitor to go at the top, which basically brought the two copper pipes together, which overlapped to give them some capacity. And then he had a copper surface on the two plastic printed pieces there, which created the tuning capacitor, and then a little knob at the bottom there so he could do the tuning with it. Made a great tuning capacitor. Nice little design here for a tuning capacitor for a mag loop. Just turning the knob gave you great tuning, and it gave you nice, pretty fine tuning. It was a nice tuning capacitor, and it brought the two plates together for tuning. And by the way, this is the Magloop uh, piece of software that you can get. This is a great calculator if you like to do mag loops. All of these are active. When you move the sliders there at the bottom, see them there at the bottom, down here at the bottom of the thing, you move these sliders, all of these curves, which show you all the various characteristics of the loop, sizes and everything, all of them actively change when you drag the sliders. So you can do wonderful design work with mag loops, and you can see what you should do to get an efficient and optimized magnetic loop instead of doing all of the poor designs you see on the internet. So if you want to get one of these calculators, download my slides and get one of them if you're a mag loop builder. And don't build one of these terribly designed mag loops you see on the internet. So here's his little design that my good buddy X0XL designed. You can see his tuning device. And what was it? He had a nylon screw that went through with a tuning knob there to bring the two plates together. That's a nylon screw going through the two copper pipes at the top on his 6 meter, 10 meter mag loop. And by turning the screw, he could easily tune this little magnetic loop that he had built. And it worked fine. It worked absolutely fine until he put RF power to it. He put 50 watts into this magnetic loop, and that nylon screw in the middle between the magnetic loop. And surprise, surprise, here's what happened. His 50 watts into his thing, his nylon screw didn't like the RF because nylon is a polar plastic. And he got a nice little jet of nylon coming right out of his nylon screw. You can see the way the thing worked. 2 foot 5/8 inch OD soft copper with coarse and fine tuning for 6 and 10 meters, and you can see the copper sheets on his nice 3D printed and his fine tuning and coarse tuning knobs on this very brilliant little design. Unfortunately, he used a nylon screw. What he needed to use was a polypropylene screw or a high density polyethylene screw, and this thing would have worked fine, but the nylon screw did not work. It was an excellent design, and it gave him great tuning and so forth. Here's a little plot of it. Now, so we decided that it might have been better to replace the top pipe in the mag loop that I have been showing, made out of PVC and metal tape, to replace the top pipe with instead of using PVC, to use PEX. Now, PEX is not PVC. PEX is high density polyethylene, and that's a good RF plastic. That's a non-polar plastic. So I've been in the process of modifying my loop to use a PEX pipe on the top, which is a much better plastic. So we learned a pretty painful lesson from studying the plastics. By the way, plastic bottles, which you can buy for the outside capacitor instead of using PVC, are made of high density polyethylene. So I've been playing with using plastic bottles made of high density polyethylene, which you can easily get them off the net. You just cut them and cut the ends off, and you get these wonderful half round high density polyethylene bottles, which make good capacitors with a piece of aluminum foil tape on them for the outside capacitors. PVC is fair to be used for these mag loops on the outside as capacitors. And by the way, never use the black ABS. for any of this, any RF work. Why? Because it's got carbon in it. Carbon to get rid of the UV sensitivity. Never use black drain waste vent pipe. It's PVC, yes, or ABS, but it's got carbon in it to make it not sensitive to the ultraviolet. So if you're going to use PVC, okay, but I prefer PEX plastic now. So use PVC, use polyethylene tubing if you possibly can. Now, here's a final thought. I just got this the other day. Somebody suggested to me, how about rain sensitivity in an antenna? Just a wire antenna, for example. Suppose you were to coat the wire with polyethylene. Would that reduce its rain sensitivity? I think it might. Polyethylene, remember, is a nonpolar plastic. I wonder if this is a question. I don't have an answer to this one right now. If you put up a wire antenna with vinyl plastic on it, and vinyl is a polar plastic. Vinyl is a polar plastic. Polyethylene is not a polar plastic. I wondered if you would put polyethylene tubing over the top of plain wire, would it be less rain sensitive? I don't know, because remember, rain is polarized. Water is a polar material. Suppose you would put polyethylene tubing over plain copper wire. Would that make it less rain sensitive? I think it just might. I want to test that one. Anyway, I know that's a bit of some eye-opening stuff, and it's still very experimental with me. I don't have all of the answers here, but at least that's something to ponder about and to think about, and to think about what plastic you might be wanting to use if you're building antennas using plastic. And there's my website, and you can download the slides if you want to from my website, w6nbc.com/slides. And there's my QR code up there to get to me if you want to.
Thank you, John. That was wonderful. It's interesting. You've got me thinking now, because one of my go-tos for ugly balins is using Nalgene bottles, just as a form, like the longer 1.5 liter ones that seem to.
What is Nalgene? I've heard the term.
A type of drinking bottle. They used to be made. They were made in polypropylene at one point, and then they changed it over because it would be less porous to, gosh, I guess a polycarbonate.
Let's search the screen here and find out.
Yeah,
I'd like to know.
Okay, well, thank you, folks. I'm going to end the recording now. We'll go into Q&A.